For nearly a century, cosmology has described a universe born in fire, expanding through space and time, dominated by unseen components. The lambda CDM model has been extraordinarily successful, but every model rests on assumptions. What if cosmic redshift has another origin? What if time itself is not what we think it is? This is the Exochronous Universe, rethinking cosmology from first principles. In the last episode, we explored one of the most important observations in modern astronomy. The light from distant galaxies arrives shifted toward longer wavelengths, a phenomenon known as redshift. Within modern cosmology, this redshift is interpreted as evidence that the universe is expanding. But what does that statement actually mean? When cosmologists say that space itself expands, what exactly is expanding? Is space a physical substance? Are galaxies flying through it? If everything is expanding, why aren't atoms getting larger? Why doesn't the solar system expand? And how can distant galaxies appear to recede faster than light? These questions lead us into one of the most subtle ideas in all of cosmology. Not how objects move through space, but how space itself is described. There are two fundamentally different ways in which objects can become farther apart. The first is familiar. Objects move through space. A car travels along a road. A spacecraft crosses the solar system. A galaxy drifts through intergalactic space. In each case, the objects move. The space itself remains unchanged. But there is a second possibility. The objects remain stationary relative to their local surroundings. Instead, the geometry between them changes. The distance increases because the underlying coordinate system evolves. This second description is what cosmologists mean when they speak of the expansion of space. At first glance, the distinction may seem almost philosophical, yet it lies at the very heart of modern cosmology. To describe this behavior, cosmologists use a quantity known as the scale factor. The scale factor is not a force, it is not a field, it is not a physical substance filling the universe. It is simply a way of describing how large cosmological distances change with time. If the scale factor increases, then the separation between distant galaxies increases as well. This expression simply states that the distance between two widely separated points depends on a changing scale factor. As the scale factor grows, the distance grows. Nothing more mysterious than that. The mathematics is remarkably compact. The challenge lies in understanding what that description means physically. One way cosmologists think about expansion is through something called Comoving Coordinates. The idea is surprisingly simple. Imagine drawing a coordinate system across the entire observable universe. Each galaxy is assigned a position within that coordinate system. As the universe expands, the coordinates remain fixed. The galaxies stay in the same coordinate locations. What changes is the physical distance represented by those coordinates. In this picture, galaxies are not racing through space like bullets. Instead, the metric used to measure distances evolves with time. The coordinates stay the same. The scale changes. In the standard cosmological model, recession speed increases with distance. The farther away a galaxy is, the faster its separation from us increases. This relationship is known as Hubble's law. Nearby galaxies recede slowly, more distant galaxies recede more rapidly, and beyond a sufficiently great distance, the recession speed exceeds the speed of light. At first sight, this appears to contradict Einstein's theory of relativity. But there is an important distinction. Relativity limits how fast objects can move through their local space. It does not place the same restriction on how distances between widely separated regions may evolve within an expanding geometry. The photon continues to travel at the speed of light, yet the distance it must cross can continue changing while it travels. Every observer, everywhere in the universe, measures exactly the same local speed of light. Nothing in their immediate surroundings ever overtakes a light beam. Relativity remains intact. What changes is the large-scale geometry used to describe the distances between far-separated regions. The distinction is subtle, but it lies at the heart of modern cosmology. In the expanding space description, there exists a distance beyond which recession speeds exceed the speed of light. Yet this does not imply that galaxies are locally breaking the laws of physics. Rather, it reflects the way cosmological distances are defined within an evolving geometry. Space is not carrying galaxies through their local neighborhoods faster than light. Instead, the separation between distant regions increases as the scale factor changes. At this point, a natural question arises. If space expands, why doesn't everything expand? Why doesn't the Earth slowly grow larger? Why don't atoms become bigger over time? Why doesn't the solar system drift apart? The answer is that local forces dominate local systems. Gravity binds galaxies, gravity binds planetary systems, electromagnetism binds atoms and molecules, nuclear forces bind atomic nuclei. These forces are enormously stronger than the cosmological expansion effect on small scales. Modern cosmology therefore predicts expansion primarily on the largest scales, between clusters of galaxies, across vast regions of intergalactic space, not within the structures held together by local forces. To make these ideas easier to visualize, cosmologists often use analogies. Perhaps the most famous is the expanding balloon. Imagine a collection of dots painted on its surface. As the balloon inflates, every dot moves away from every other dot. No dot occupies a special central position. From the perspective of any dot, all the others appear to recede. This analogy successfully illustrates several important features of expansion, but it can also be misleading. The balloon expands into a surrounding space. The universe does not require such an external environment. The balloon possesses a physical surface. Space-time is not literally a rubber membrane. As useful as the analogy is, it should not be taken too literally. Another popular analogy is raisin bread. As the dough rises, each raisin sees every other raisin moving away. The farther apart two raisins are, the faster their separation increases. This resembles the behavior described by the Hubble relation. But once again, the analogy has limits. Bread is a material substance. Space is not generally treated that way within general relativity. The model captures the mathematics of increasing separation, not necessarily the underlying physical reality. Perhaps the most familiar visualization of all is the rubber sheet. This image helps us picture changing geometry. It encourages us to think beyond ordinary motion. Yet it too introduces complications. The sheet appears embedded within a higher dimensional space, an additional dimension that plays no role in the mathematics itself. Every analogy illuminates certain aspects of the theory and obscures others. This brings us back to an important distinction. What do astronomers actually observe? They observe photons, spectra, redshifts, brightnesses, angular sizes, patterns in the distribution of galaxies. These observations are real measurements. The expansion of space is the geometric framework used to explain them. This framework has been extraordinarily successful. It provides a coherent description of a vast range of observations. But it is still a model, a mathematical interpretation of physical measurements. and science advances by continually examining how observations and interpretations relate to one another. The idea of expanding space sits at the foundation of modern cosmology. It shapes our interpretation of redshift, it influences our understanding of cosmic history, and it plays a central role in explaining the relic radiation known as the cosmic microwave background. But important questions remain. How directly do observations require expansion? Which conclusions follow inevitably from the data? And which arise from the particular geometric framework we use to interpret that data? Those questions will accompany us throughout the rest of this series, because before we can compare competing cosmological ideas, we must first understand what any successful cosmological model is required to explain. That will be our next step.